Okay, for this approach, I'm going to use something called the voltage divider equation. Earlier, I have explained you using the current divider equation, but that's not in the syllabus. The voltage divider equation is mostly seen in the syllabus, so I will explain using that. So first of all, they have given that each resistance has a value of 2 ohm, right? So we can find the total resistance in the parallel circuit, which is 1 over R total is equal to 1 over 2 plus 2. Why 2 plus 2? Because this is in series, plus 1 over 2, this is equal to 1 over 4 plus 1 over 2, and this is 4, 1 times 2 times 3 by 4. But remember, 1 over R total is equal to 3 by 4, so R total is equal to 4 divided by 3 ohms, right? So this one over here, the total resistance in this circuit is equal to 4 by 3 ohms, right? So now what we have to do is we have to find the total voltage across the circuit, right? Here the voltage is 2 ohm. Now I can make this one, right? I can make this one, and I can say that all of the resistances together, right? B plus C plus D is 4 by 3 ohms. So I can say that this whole circuit is 4 by 3 ohms. So using the voltage divider equation, I can find the potential difference across this circuit, the potential divider across this circuit. So the voltage across the resistor A is equal to the total current multiplied by the resistance value of that particular voltage, which is in this case 2, divided by the total, which is 2 plus 4 by 3. This is 10 multiplied by 2 divided by 10 by 3. So I can write this like this. This 10 and this 10 cancel, so this has to be 6 volts. So the voltage across the resistance A is 6 volts. According to Kirchhoff's second rule, which is the voltage circuit rule, the sum of the EMF around any closed circuit loop is equal to the sum of the potential differences in the same loop. So when this has to be 6 volts, then this 6 plus what will give you 10, 6 plus 4 will give you 10. This should indicate that the total voltage in this circuit over here has to be a value of 4 volts, right? Has to be a value of 4 volts, right? So now what we are going to find is they're going to find the individual voltages. They're going to find the individual voltages, and using the individual voltages, we're going to find the individual power dissipation in each of the resistors. Now if you look at this whole circuit has a voltage of 4 volts, and in parallel the voltage is the same. That means the voltage across these two resistances is equal to the voltage across these two. So since these two has a total of 4 volts, we can say that here there are two resistances, so there's a lower share of the voltage, so the voltage is divided equally between them. This has to be 4 volts, and this has to be 4 volts, and this is 4 volts, right? So this is 6 volts, 2 volts, 2 volts, 4 volts. We know the resistances. We can find the power dissipated in each of the resistance. Now the power dissipated in A, I'm going to use the equation V squared over R. In the earlier method I explained using the current divider method. So this is equal to V squared divided by R. The voltage is 6, so 6 squared divided by 2, 36 divided by 2 is 18 watts. Okay, the power dissipated in B is V squared divided by R. V squared is 2 watts divided by 2, so this has to be 2 watts. The power dissipated in B is equal to the power dissipated in C. Why? What's the reason? Because the voltages, which is the total voltage of the circuit, which is 4 volts, is equally shared between the two resistances 2 and 2 respectively. So I can write this that the power dissipated in B is equal to the power dissipated in C, so this has to be 2 watts. Now the power dissipated in D V squared over R is equal to 4 squared divided by 2. So this has to be 4 squares. 4 squares divided by 2 is 8 watts. Now